Hello everyone, my name is MOSFET, and in this video we are going to discuss the thermal drain noise in a MOSFET. We're also going to discuss the gate noise of a MOSFET and the correlation between the thermal drain noise and the gate noise. And finally, we will also look at the small signal models of a noisy MOSFET. So let's get started with the thermal drain noise of a MOSFET. Now, before we start, in the previous video I discussed the thermal noise in a resistor. And so the idea from that video was that if you have a conductor, the electrons are not going to flow straight through that conductor. They're going to have some sort of random motion, and that random motion creates thermal noise. And if you want to have as low of a thermal noise as possible, you should cool down the electronics to make them as noise proof as possible, especially when it comes to thermal noise, right? And so in a similar sense, we have thermal drain noise in a MOSFET. So in a MOSFET, MOSFETs can be thought of as voltage controlled resistors, right? And in a typical MOSFET, so for example here I have a typical NMOS, we have this channel, right? And when electrons are flowing through from the drain implant to the source implant, they're also going to pass through this P minus region, which is the channel. And of course, again, they're not going to flow in a straight line like I've shown here. They're going to bounce around, and they're going to have some sort of random motion while electrons or charge carriers in general pass through the channel. They're going to have some sort of random motion, and which causes thermal drain noise in a MOSFET. So again, similar idea as thermal noise in a resistor. And when we look at expressions, the thermal drain noise in a MOSFET can be written as 4kT gamma GD naught B, where B is the bandwidth. So in some textbooks, you might even see delta F instead of B. So it's just basically the bandwidth. GD naught is the drain source conductance at VDS equals 0. And gamma is the excess drain noise factor. And you can use a value of 2 by 3 as a constant. So another thing I wanted to mention is, GD naught, this drain source conductance, which is GDS, at VDS equals 0. And if you do that derivative, basically GDS is like a derivative of the drain current with respect to VDS, right? And so if you take that derivative and then you insert VDS equals 0 in that partial derivative, what you'll end up with is an expression which equals GM. And so if you sort of, replace GD naught with GM in this previous equation that we talked about, then you get this final equation, which is the average drain noise current, and that's 4 kdB GM gamma. And so if you're taking away expressions from this video to use in your noise analysis, this is the expression you wanna use. So that is basically the drain noise in a MOSFET, the thermal drain noise, and alternatively you can use the voltage representation of the thermal drain noise in a MOSFET. Okay. All right. So that is the thermal drain noise, and now we'll talk about the gate noise in a MOSFET. So we talked about how there's channel in a MOSFET, and the channel has some sort of thermal drain noise. We just talked about that, but as it turns out, the gate of a MOSFET is capacitively coupled to the channel, which I've shown here in the pink. And so if you have any noise in the channel, turns out that some of that noise will get capacitively coupled, and it will show up at the gate terminal of the MOSFET. And so that basically is the gate noise of a MOSFET, and it's induced because of that thermal drain noise. Okay, and for the expression, the gate noise current can be written as 4 kdB delta G sub G, and here delta is gate noise coefficient, and you can use a value of 4 by 3, which is a constant, and G sub G is another expression which is dependent on the frequency squared, CGS squared, and 5 over GM in the denominator. So again, if your CGS is large, that means your gate noise will be higher. And another important thing to note here is the frequency, the dependency on frequency. So if you have at higher frequencies, the gate noise is going to be higher, which is important because at lower frequencies, usually we don't consider, for analog kind of circuits, usually we don't consider the gate noise. But if you're doing like RF design and stuff, or any higher frequency designs, gate noise is a big concern. And so you want to model this IGN noise for your analysis, which is very common for like RF designs. All right, so that was the gate noise, and let's look at the small signal model for noisy MOSFETs. So uh, you have seen this small signal model before, but now we included this thermal drain noise in a MOSFET and the gate noise. So that's for the NMOS, and for the PMOS, again, same thing. That's the thermal drain noise, and that's the gate noise. All right. So essentially, what we'll do in later videos is basically whenever we have to analyze the noise of a MOSFET, we'll include these drain noise and gate noise in the small signal model, and then we will analyze the noise in the circuit, and we'll see how much of this noise shows up at the output of a circuit, and then we will talk about input preferred noise. But all of that for a later video. But for now, all I wanted to say is that including noise in or doing noise analysis is as simple as you take the small signal model of a MOSFET, and then you include this drain noise and gate noise in your small signal model. All right, now let's talk about the correlation coefficient between the drain noise and the thermal drain noise and the gate noise in a MOSFET. So essentially, previously we talked about how there's thermal drain noise, and because there's thermal drain noise in the channel, some of that gets capacitively coupled and induces the gate noise, which means that the origin for the drain noise and the gate noise, for the thermal drain noise and the gate noise is the same, right? And which means these two noises are correlated. And so this is the correlation coefficient, C, and it's basically the IGN conjugate multiplied by the drain noise, and in the denominator we have the square root of the mean squared gate noise and drain noise. So that correlation coefficient is equals to 0.395 J. And for now, you can just treat it as a random fact. But later on, when we analyze circuits and we're modeling both the gate noise and the drain noise, you'll see that there's points in your derivation where you'll make use of this correlation coefficient between the drain noise and the gate noise. Okay, so before we end this video, I wanted to add another note that noise is a pretty deep topic. And so, you can go read more about the thermal drain noise and the gate noise and flicker noise and shot noise and popcorn noise and burst noise. And, there's other kinds of noise, avalanche noise, all these KD over C noise. Oh my God, there's so many noise, sources and stuff. And so it's good to know, noise in a more comprehensive way. When you're, so that you know your noise sources when you're designing your circuits, and what kind of noise sources would be the most prominent for your particular application. Now, one of the resources that I found helpful was this book by Thomas Lee. The title is The Design of CMOS Radio Frequencies Integrated Circuits. So I have the second edition, but you can use that, or you can also read about noise from the book by Gray Mayer, or there's also text by Razavi. All of these texts would usually have some sort of discussion on different kinds of noises, and you can also use the internet. I mean, there's different. I've seen slides from different universities about noise, and other YouTube videos as well. So definitely encourage you to look at different kinds of noises. And what we discussed in this video is I would say that this is just like scratching the surface, right? I'm trying to get us to a point where we can analyze circuits, and we can look at the noise contribution from all these noise sources at the output, and calculate the input preferred noise. That is our goal, and I'm trying to get us to that point. So in this video I've mentioned a few quick facts about the thermal drain noise and the gate noise and the expressions that you need to know. and the cause of those noises. But just wanted to mention that it's a pretty deep topic, and yeah, there's resources available if you want to go deeper and learn more about noise. So that is pretty much it for this video, and I'll see you in the next one. Cheers.